Okay, in this video, I'm continuing this derivation of the expectation value of the position cubed transforming state 2 into state number 3. And I left the all the derivation that we did before on the page. And what we ended up with was that we're going to save 3 of the 8 terms because this x cubed operator is really h bar over 2m omega to the 3/2 power a plus a dagger cubed. Okay, so and so we worked out all 8 terms. The only terms that survived were term number 4, which was a dagger operating on 2, which we said was 4 square root of 3, the third state. So that was the 4th term. The 6th term was a dagger operating on n equal 2, which gave me a 3 square root of 3, the third energy level. And then the 7th term, which was a dagger a, operating on 2, which gives me a 2 square root of 3 on the third energy term. Okay, so now let's put it all together. We basically have 3, let me step back. We basically have h bar over 2m omega to the 3/2 power 3 product of 4/3 plus 4 square root of 3, 3 square root of 3 plus 2 square root of 3, 3, which gives me 4 plus 3 plus 2 is 9 square root of 3. 3 product of 3 and 3, which is 1. So this expectation value of the position cubed going from state 2 to state 3 has a value of 9 square root of 3 h bar over 2m omega to the 3/2 power. So it's still kind of a lengthy derivation. We had to go through 8 different terms to work them all out. But we saved ourselves in 2 ways. One, we saved ourselves from doing the really big integral with the Hermite polynomials, and times x cubed times the e to the minus x squared thing. And so, in this case, it was all just algebra. So it's a question of solving the problem with algebra versus solving the problem with integration. The second thing, which is probably a little more interesting, is the fact that we did not know, so no wave functions involved. So we didn't need to know the wave function. We didn't actually have to solve the wave function to figure out that it was a Hermite polynomial. Instead, it was all just working with vectors, vectors that represent the energy, and it was just going from a transition of 2 to a 3. So really, it was implementing orthonormality and the raising and lowering operators. You don't need to know the shape of the wave function. You don't need to know it. So what we're left with is now 2 different ways of trying to solve the harmonic oscillator. And so this is why The harmonic oscillator is such a great example of how you can solve the problem with the Heisenberg-Dirac approach, where you write everything in terms of vector states, and then you have operators, and then you apply a lot of linear algebra to apply those operators to the states to get an answer, which you can then compare with the experiment, or the Schrodinger approach, where you just set up the Schrodinger equation with which becomes the second-order differential equation, which you can then solve, and then once you solve it, you get the wave function, and then with the wave function, then you can then calculate things like the expectation value. So both ways are legitimate. Actually, all three of them, Schrodinger, Heisenberg, and Dirac, won the Nobel Prize in the exact same year because it was shown that those methods that they used were equivalent. Whether or not you wanted to use linear algebra and the Heisenberg-Dirac operator approach, or if you wanted to use the Schrodinger wave function approach, you can then get the exact same answer. And so really it's a choice of what you want to, how you want to solve the problem. Whether or not you want to know the wave function, or whether or not you would just like to use operators on vector states in order to solve the answer.